Bismillahirrahmanirrahim. So last time we talked about the techniques in the category of controlled access, and we said that for controlled access we have a centralized controller that arranges and maintains the access to the shared medium. Therefore, we can easily eliminate collision. And we talked about two techniques in that category: the reservation, where the controller will be responsible for granting the reservation for the shared channel to a particular station through the reservation phase. And then based on the reservation phase, we can optimize the transmission phase by granting the access to subset of the stations that happen to have data at that time. The other method is through polling. Polling is like the controller will select a particular node to send this node some data, or it will pull in a specific order all the nodes to ask these nodes whether or not they have any data. So of course, the challenge of having a centralized controller is always the fact that we can run into a single point of failure. So this controller, if the controller is not there, then the meeting is off and everything is down. The whole network is down. So channelization talks about the fact that we need to eliminate collision while not using a centralized controller. But in that case, the idea is that we have to preset the shared medium and divide it in a certain way at the beginning of the communication, and this configuration stays fixed. بمعنى إنه we can divide the channel into frequencies or into time slots, and we fix that all the time. Okay, so we'll talk about three major techniques in this category. One is to divide the channel into frequency domains. Two is to divide the channel into time domains or time slots. And three is to divide the channel into codes, which is a new method that you have not been introduced to this before. In fact, CDMA or code division multiple access is the dominant technology for 3G. And it stayed like that for decades until 4G came with another revolution, which is called OFDMA, which is similar to this, but with orthogonal frequency. So we'll not cover this in the course, so we'll cover only these three techniques. So for MA, we simply divide the whole bandwidth of the network into channels, and we divide the channels in such a way that it's fixed. So we have to divide the bandwidth into fixed number of frequency ranges. Okay, so each station that comes in will select one of these channels, and we'll use that frequency range to send any data. So then if these nodes are sending at the same time but on different frequencies, we know that a collision will not happen. But the problem with that is that we have to fix this, which means if a node goes out of the network or stays silent for some reason, this frequency range is not going to be used. Okay? So the advantage of this is that we don't need a centralized controller. We have no collision. So these are advantages. But the disadvantage is if the node is not using any frequency range, then this frequency range is going to be wasted. It's part of the bandwidth that nobody's utilizing it. Another problem here is the fact that at the if all the nodes are sending on the channel, this is the composite signal that you get, right? The composite signal is like it's a composite of all the transmission from all nodes. So if a node wants to receive a signal, let's say from station 1, it needs to apply a filter on this channel, right? However, as we know, the filters are not like this. Filters are not ideal. So they are like this. So because of the imperfection in the filter design at the receiver side, we need to have some spaces in between these channels that, again, these are overhead that we cannot use. Okay? So we call these guard bands. These guard bands are gaps between the channels that are used by each station that cannot be used for transmission, which is an overhead. Okay? But we need to have these guard bands to account for the imperfection of the receiver. So that's the disadvantage for the case of FDMA, is that we have to divide the bandwidth across the channels. If one of the stations is not using the channel, we waste it. And of course, we need to have guard bands. So in that case, the available bandwidth is going to be divided in the frequency domain as separate channel, and we need to separate that by guard bands. The other way of dividing the resources of the channel is through TDMA, or time division multiple access. In time division multiple access, instead of dividing the channel in the frequency domain, instead of dividing the entire bandwidth of the network into channels, all the bandwidth of the channel is going to be used by all nodes. However, in the time domain, we have to assign time slots to each node or a station. And again, this is fixed. So prior to the meeting, we say that, okay, we're coming to this meeting. Each one of us will have 5 minutes to talk. Okay? And then, if a person does not have anything to talk about, we have to wait for these 5 minutes because the other person is waiting for his time to come. And these 5 minutes, we have to stay silent and nobody's talking, nobody's using the floor. Okay? So everyone is assigned a specific time to talk. So the problem, do we need guard bands here? No. Yes. Why بقى? Not بقى in the, not just in the synchronization. Remember here, guard bands here account for the propagation delay, because these nodes are located in different locations. And whenever you send a signal, the signal propagates, okay, and it takes time to reach to the different nodes. So we need these guard bands to account for the propagation delay across the shared medium, regardless of the location of this node on the shared medium. Okay, so we still need guard bands. So it's like FDMA. In fact, here we have another problem related to synchronization, because calculating the time of the transmission for each one is based on its own clock. And again, synchronizing distributed clocks across nodes is actually a big issue. And we need to have some techniques to synchronize the clocks of all these nodes so that the time that each node calculates will be globally correct. Otherwise, if some of the clocks is drifted a little bit, a node will start a little bit early of its time or a little bit later, in which case it will collide either with the one before it or the one after it. Of course, that's another reason why we need to have guard bands. Okay? So guard bands are going to be used for this, and also we can use other techniques as like self-synchronization through the specific line coding schemes in sending the signals in order to also help synchronize the clocks across the different stations. So that's the disadvantage in the case of TDMA. So we still need guard bands, not only to account for the propagation delay, but also to account for the imperfection in synchronizing the clocks across the different stations. Okay? Type. So here, the bandwidth is just one channel, but we divide this channel in the time domain. And we still need to have guard bands. So now, we talk about a third method, which I don't think it has been introduced to you before. which is CDMA, or code division multiplex. So we said that if two nodes want to send at the same time, they need to use a different frequency, right? If they send at the same time, but they're using two different frequencies, then they will not collide. So the question is, can we have two nodes sending at the same time at the same frequency? Well, so far we have not been introduced to such a thing. So imagine if we have a room like this, and there is two synchronizations happening between two pair of people. So I'm talking to Wahab, for example, and Muhammad is talking to Abdullah. Okay? So if these two conversations are happening at the same time, with the same volume, more or less, so one in the back of the room will not be able to distinguish one from the other. Right? So typically, you will not be able to. So we call this interference, especially if the two conversations are in the same level, you will not be able to extract one from the other. And that's what we have formulated or called collision. Okay? Imagine this same example, but me and Ahab, we know Chinese. And Muhammad and Abdullah, they know English. Okay? And the reason for Chinese and English is that those two languages are not related whatsoever to each other. They are totally uncorrelated. Okay? And imagine if someone in the back of the room, he understands only Chinese. Okay? So in that case, English will be just noise to him. And he will be able to extract Chinese from the two conversations that are happening. That's the idea of CDMA. So when a node wants to send, we will code the data of the node in Chinese. Okay? And if another node wants to send, we'll code this in Persian, for example. And then we'll code another data into English. So these languages are designed in such a way that we call them orthogonal to each other. They are not related in any way. Okay? So if someone on the other side, he understands only Persian, he will be able to extract Persian. If he understands English, he will be able to extract English, and so on. فهمنا كده? So that's the simple idea of CDMA. So how can we prove this and mathematically? So imagine if we have 4 different stations. So we have station 1, 2, 3, and 4. So we'll take the data from station 1, we'll code it by multiplying the data by a certain code. Okay? And we'll do this from each station, and then we will send at the same time at the same frequency. So these codes, they have 2 very important conditions. Very, very important conditions. One, any code multiplied by itself will always lead to n, such that n is the number of stations. It's a high number. And this indicates that the code has very high correlation with itself. 2, any 2 codes such that I is not equal to j is 0. Which means that these codes are orthogonal to each other. It's like English and Chinese. They have no relationship whatsoever. Okay? So these codes are designed in this way. If that's the case, then if any node, say node 5, any of these nodes wants to receive the data from node 2, for example. So this node needs to have the code of the language that station 2 used to send, which is C2. So this node will take C2 and then will multiply it by the composite signal. So now we have, this is the composite signal, which has all the coded languages all together, right? right? So all the coded languages, they will be lump sum together and then will be sent on the channel, because we're saying that this is at the same time at the same frequency. Okay? So by just taking this code and multiplying this code by the composite signal, what is the result? C2 multiplied by D1, C1. What is the result? 0. C2 multiplied by D2, C2, D2N. So all the items will be 0 except for the data from station 2 will be amplified. So it becomes D2 multiplied by N. So it becomes amplified. Okay? So that's the idea of CDMA in a nutshell. It's very, very simple. But using this simple idea, as I said before, this is the dominant modulation scheme in 3G. All 3G is based on CDMA. ماشي؟ طبعا, of course, it's not that easy. It's not that ideal. We'll talk about the silent node will not contribute to the composite signal in any way. So the data multiplied by whatever code, the answer is always 0, which means that this node is not contributing to the composite signal in any way. So these are the codes. So we need to see whether these codes, they fulfill the two conditions we talked about or not. The first condition is that each code is highly correlated with itself. So by multiplying the code by itself, يعني 1, 1, 1, 1, 1, 1. Okay? And then we multiply one by one. It's a simple dot product. يعني. So the answer is 4. Here, the answer is 4. For all of them, the answer is 4. بمعنى ان احنا we only need to avoid using zeros here. If we use zeros, 0 multiplied by 0 is 0. So the answer will not be n, which means that 0 will account for the fact that the correlation will not be that high. Okay, so we just need to avoid using zeros, which means that all the data will have to be converted into ones and minus ones, so that we maximize the correlation. ماشي كده? So this is easy, and this is fulfilled in all these codes. The other condition is if you multiply any two codes, the answer is always 0. So we multiply here 1 minus 1, 1 minus 1. Answer is 0. You try it on the C1 and C3, the answer is always 0. So any two codes, the multiplication, the dot product of these codes is always 0. ماشي? So it's simple. So the first thing we need to do is the data from each station, it has to be first converted into ones or minus 1. ليه? As we said, we need to maximize the correlation. So we don't need to use zeros except if the node is silent. Because 0 multiplied by anything is 0, which means that طيب. So that's easy. So using بقى numbers, if we have 4 stations, then we need to have codes of size 4. The code will be of size 4. So 0 will be converted to minus 1. We multiply minus 1 by the code, so the answer is all minus 1. So we'll do this for station 1, 2, 3, and 4. 3 is of course silent, so 0 multiplied by anything is 0, so we don't need to add anything for station 3 because it's silent. It doesn't want to send anything, neither 0 nor 1. ماشي? So once we do this, we just get the summation of these 3 to get the composite signal. So minus 1 plus minus 1 plus 1 is minus 1. Here, minus 1 plus minus 1 plus minus 1 is minus 3. So it's a straightforward summation. ماشي? Any questions? تمام كده؟ طيب, so this is the composite signal. So that's That's how it looks like in the signal representation. Using signal representation, this is how it looks like. So when station 1 wants to send 0, 0 will be -1, which will be multiplied by the code. So it becomes all -1s, which is, as signals, it becomes like this. So in the time domain, these signals, digital signals عادية يعني, and then we sum them up. So from station 1, 2, and 4, station 3 does not have anything to send. So we'll add 1, 2, and 4. So the answer is, this is the digital signal that will end up being on the line. ماشي? Straightforward. طيب. Then بقى, if any station, any of these stations, or any حتى station number 5, wants to receive data from station 2, ماشي? Station 3 wants to receive data from station 2. So it needs to use the code from station 2, which is 1, 1, 1 minus 1, 1 minus 1. Which is in terms of signal representation, it looks like this. Then we multiply again this code by the composite signal. So 1 times -1 is -1. -1 times -1 is 1. And then -3 times 1 is -3. And then -1 times 1 is -1. What is the summation of all these 4 values? Is -4. ليه بقى احنا بنعملها كده? Why do we do it this way? In receivers, we typically use what we call integrators. Integrators are hardware devices that actually it gets the summation of these values by accumulation. So this is -1, which means that we go to the negative -1. Then 1, which means that we go up 1. And then we go down -3, and then we go down to -4. Okay? Why? Because actually, in reality, these signals are not idealistic like this. They have noise and they have other things, right? So these are signals. Here we talk about digital signal, but in reality, these digital signals, they have noise, they have distortion, they have other things. So they use integrators to integrate. So you may actually end up with -3.7 or 4.2 or something like that. But in all cases, it's fine, because anything in the negative, معناها the original data was 0. Anything in the positive, it means that the original data was 1. So it's easy. And the difference is actually way in the negative. That's why we say it has high correlation with itself, so that we can distinguish easily between the bits. Okay? طيب. We'll start to have tricky numbers that might actually affect if one of these signals has low amplitude, okay, compared to the other. So we might end up with some gray levels and some boundary levels that it will be tricky. Okay, so that's it. So this is the idea, and that's how we do the CDMA. So the question now is that, is there a systematic way of generating these codes so that it fulfills those 2 conditions? And the answer by Walsh is yes. It's very easy, actually. We call this code chip sequences. So in many cases, we call them chip sequences or CDMA codes, or CDMA chips. So all these names are for the same thing. And the idea is very simple. You start the Walsh matrix. It has a size of power of 2. So there is no Walsh matrix of size 5 by 5 or 7 by 7. It has to be in power of 2. ماشي? Of course, there are some techniques that we can still use 5 and stuff, but that's not the straightforward method of Walsh. Walsh talks about size of power of 2. If we agree on this, then generating these codes will be a very, very, very simple job. Very simple job. You start by a matrix 1 by 1, 1 by 1. Okay? And then all you need to do is to create another matrix of double the size only by replicating the same matrix 3 times in this triangle direction, and the fourth one will be a toggled, multiplied by -1. Why? If you do the dot product, Wn multiplied by Wn is Wn. Wn multiplied by minus Wn is minus Wn. So if you get the summation, it's always 0. So this is what we say the product condition. Okay? So if we do this on any size that's double of n, double of 2 يعني, that doubles all the time, then this rule will be maintained all the time. Okay? And we can do it recursively. So if we want W2, we take W1, and then we repeat it 3 times, and then the fourth one will be multiplied by -1. What about W8? W4 by 4. So it's like we get this, we repeat it here, here, and here, and we get this one, and we multiply it by -1. If we want 8, then we repeat the same matrix 3 times, and then the fourth one we multiply it by -1. So if this is the case, then we generate a Walsh table of size 2 to the power m, okay? And the codes in this Walsh table always fulfills the 2 conditions we talked about. High correlation with itself, and no correlation with any other code. That's it. Okay? Start to have. So then the number of sequences in the Walsh table is if of power of 2, so it's 2 to the power m. So if we want to find the chips or the CDMA codes for a network with 2 stations, easy, we talked about it, 1, 1, 1, -1. That's easy. So for 4 stations, we repeat this, so it becomes 1, 1, 1, -1, 1, 1, 1, -1, 1, 1, 1, -1, and then -1, -1, -1, 1. Okay? So if we have 4 stations, then we get each line, each row, يعني each row in this matrix, and we assign it as a code to 1 station. Okay? So we take each row and we assign it to 1 station as this is the CDMA code for. However, for reception, for receiving the data, the node may need to have all the codes. Right? بمعنى يعني if you in the example we talked about, 2 people are talking Chinese, 2 people are talking Persian, 2 people are talking English, and so on. So if you want to understand English, you need to have the code of English. If you want to understand Chinese, you need to have the code. So a node that wants to receive from multiple nodes needs to have all the codes of all the nodes that it wants to communicate with or it wants to receive data from. ماشي? So reception. What if we have 90 stations? We cannot have a Walsh table of 90 by 90. We know that. So it has to be of size A. So the codes need to be of size 128. Okay? So for that size, 38 codes are not going to be used, which we can use them for future growth of the network. Okay? The only issue with this is that the receiving nodes will need to have all these codes. Okay? All the 128 codes in order to be able to receive from any node at any point in time. So that's one of the disadvantages of CDMA, is that for a node to receive from multiple nodes, it needs to maintain all the codes for all the nodes that it wants to communicate with. Another issue with with this CDMA بقى, which is a little bit tricky. So imagine if for the example that we talked about again, if you have Chinese and English, and then the two conversations are happening at the same level more or less. So one in the back will be able to extract Chinese from English or English from Chinese with very high accuracy. However, if one language is with low volume, the other language will constitute some kind of a interference, very high interference on this. بمعنى ان accuracy, the nodes need to maintain the signal levels at the same level, more or less. But who can guarantee this, especially in wireless? Especially in wireless, we said that the attenuation is very significant, right? And the attenuation in multiple directions is very significant. So the only way for you to adjust the signal level is that you have to have some power adaptation or power allocation from the transmitter side, which actually increases the complexity of the transmitter. ماشي؟ يعني this issue is a little bit يعني advanced, مش مشكلة يعني if you don't get it it's okay. بس يعني the idea is that again if one of the languages has low volume, the other language will form some kind of interference, and this language might be at a disadvantage and will not be received with high accuracy at the receiver side. So these are some of the problems of CDMA. So basically CDMA is very good because you can have multiple nodes sending at the same time at the same frequency. So the bandwidth is used for all the nodes. In fact, this is very, very attractive in cellular systems in particular. ليه بقى؟ لأن for cellular systems, FDMA is very complicated. You have to maintain lots of frequencies and you have to arrange which channel support which frequency. It becomes really يعني at a global level it becomes really hard. CDMA, all the base stations, they can use the same frequency, they can use the same thing. And there's no synchronization at the data transmission that's required. There's no need for guard bands, nothing. Okay? So it makes it much more attractive to use CDMA, and that's why, as I said, it's the predominant technology for 3G.
So CDMA for small networks and CDMA for big networks.
ليه بقى? Why?
Wireless range or Ethernet range is very, very small. Like 3G is worldwide.
You mean like for this level issue in CDMA, if the network is very large, then CDMA is not good?
No, I mean, is it or not?
لا, this is not the case really, because as I said, it's in cellular system the range is very large. But what I'm saying is that you need some power adaptation at the transmitter. يعني بمعنى ان انت if you want someone in the back of the room to receive what you are transmitting, then you need to adjust your voice level so that it goes there at the same level like anyone else. يعني you need to make sure that if he wants to receive whatever you are sending, then the Chinese language needs to have higher volume. Okay? If someone close to you, then if you lower the volume a little bit, so it's okay. It's okay, because the other conversation is far anyway. And the idea is that at the receiver side, the level of the two languages needs to be more or less the same. Okay? So if you are closer to the person and the other one is far, he has to worry about sending with high power, and you can send with low power, so that both arrive at the same level at the receiver side. Okay? So you need some power adaptation. You need to adjust the power from each node according to where the receiver is. And that's tricky in some cases. That's tricky in some cases, but in cellular systems, it's يعني we know how to do this. But it just adds a little bit of complexity on the transmitter. In addition to the complexity of the receiver, because the receiver needs to have all the codes. But having all the codes is easy. It's just, يعني, these codes, they are not secret. And actually, one of the attractions of CDMA is that these codes, they can be used as keys for security حتى. If you have very large pool of codes, then the nodes will not know exactly which node uses which key, except the ones that you want to receive from. So it's some kind of يعني, implicit security. يعني. But يعني, that's the main idea of CDMA in general. And as I said, it's attractive. This is the proof, of course, for the proof that we did before, that if a node wants to receive the code from station 0, all it needs to do is just to use the code for, station 1. It needs to use code 1. If you multiply this by the composite signal, the result will be D1 multiplied by N, which we did before. So that's an indication that you can extract one particular signal from the composite signal, even if you are sending multiple signals at the same time at the same frequency, but using the codes. ماشي? So that's the end of this chapter.